First of all, I would like to thank the Toruń division of the Polish Physical Society for organizing this amazing event. Yeah, that's quite privilege for me to give a talk in this seminar. Thank you for the invitation. So in nature there are several simple systems that can be calculated from the first principles of quantum mechanics extremely accurately, and this opens possibilities not only to test quantum theory at extraordinary level of accuracy, but also, as was nicely pointed out by Jacek, to search for new physics beyond the standard model. And there are the story is should start with one-body systems, elementary particles. There are few leptons that can be used for that. So this is, in principle, interactions of leptons. So I think the pointer doesn't work. Do you have a stronger one? So the interaction of electron muon, actually the tau is very short-living, and it is difficult to study tau. But this interaction of electron and muon with quantum fields is manifested as an anomalous magnetic moment. Then if we move on, then there are two-body systems with this very prominent example of hydrogen atom, which is like an anchor system for nearly whole quantum mechanics. And there are many different variations of hydrogen-like system. My favorite one is the positronium atom. So this is an amazing system that is composed only of two leptons, two elementary particles, which means that point-like charges. There is no ugly proton whose structure cannot be calculated from first principles with any reasonable accuracy. There are three body systems with the most prominent example of helium atoms, but there are also many other cases. The HD plus molecule, or an exciting case of antiprotonic helium, in which we don't know whether this is still an atom or already a molecule. So the one electron is replaced with antiproton, and so this is an atom which can actually vibrate and rotate. And finally, the list of these simple calculable systems is closed with this fourth category, and probably you wouldn't be surprised if I say that within this category I'm focused on molecular hydrogen. This is something we really focused a lot in my group. And this is a history of accuracy of H2 measurements. So it started with the works of Herzberg just after the war. And then, so this is a relative accuracy of the measurements of the vibrational lines energies. And the breakthrough happened when with the invention of optical frequency comps. And then the accuracy really, especially experimental but also theoretical, really accelerated. But if you look at this chart, you can see that there is still a huge gap between the accuracy for molecular hydrogen and the best accuracy for atomic systems. It is like almost 10 significant digits in accuracy. And the reason is the first reason is that H2 is a molecule. It is difficult to play with a molecule comparing to atom. And the second reason is that H2 interacts with electromagnetic laser fields extremely weakly. And it is technologically and also on the fundamental level, it is very difficult to talk with molecular hydrogen. We are interested especially in the ground electronic state of molecular hydrogen for two reasons. The first reason is that the ground electronic states can be calculated extremely precisely, already almost to within 10 meaningful digits, with nice perspective for further progress. And the second reason is that the raw vibrational states in the ground electronic state are extremely long-living, millions of seconds. This means that the fundamental limitation on the accuracy is really, really low. And we started in my group the adventure with molecular hydrogen a few years ago. So that would be a subject for another talk to explain exactly the experimental methods. One important thing is that the hydrogen, as I said, the hydrogen molecule interacts with electromagnetic field extremely weakly. So this means that we have to extremely strongly enhance the signal, and therefore at the heart of our setup is a extremely high finesse optical cavity, with a finesse almost 1 million. This means that the photon has to bounce almost 1 million times before leaving the cavity. And with this approach, we managed to reach 100 kilohertz level accuracy, which corresponds to testing quantum electrodynamics corrections at 5th meaningful digits. This means that in our lab, we see very clearly the influence of the virtual photons that perturb the structure of the molecule. And now to push the accuracy even further, we decided to develop a cryogenic version of such a high finesse optical cavity. So for several, no time to explain that, but for several reasons, it is very beneficial for accuracy to move the whole technology into a deep cryogenic regime. So then we designed such a double vacuum structure. This is like a vacuum inside a vacuum, a room temperature vacuum that protect us against the atmosphere pressure, and inner cryogenic vacuum, which is really the experimental chamber. And this is quite big setup. So the cavity is almost 1 meter long. This is a quite large cryogenic system. And the whole experimental system is cooled down uniformly, even down to 4 Kelvin. So this is some pictures from the assembling process. This is this huge inner cryogenic vacuum chamber, and this chamber is suspended inside a vacuum chamber on a thin titanium rods to prevent the heat leakage, but also to attenuate the external and internal vibrations. We have to remember that inside there's a very fragile optical cavity that has to be in very silent condition. So this is the just last moment before first test of the cryogenic system, and the system was designed to be cooled down to 10 Kelvin. And actually, it turned out to work even a bit better than design, because we managed ultimately to cool it down to nearly 4 Kelvin, the whole optical cavity. In parallel to developing the cryogenic system, we developed laser systems that allows us to access fundamental the fundamental vibration in hydrogen. For few fundamental reasons, it is beneficial to work on fundamental, not on overtones, but it is technologically difficult to get there. So we use the so-called optical parametric oscillation process, in which we can split the energy of a photon in a very well controlled way, such as to access this difficult to work with 2.2, 2.4 micron spectral range. We also did a good bit of really exciting engineering around this system, and one of example is this mirror position actuator. So to really operate optical cavity and to do spectroscopy, we have to have this flexibility to change the length of the cavity by few wavelengths. And it is relatively easy to do at room temperature, but this is a huge challenge to change the position of the mirror by few nanometers with the tuning range of few micrometers at 4 Kelvin. So we developed such a fancy small photonic module that can not only, so the challenge was not only to move the mirror, but the challenge was that to assemble the cavity, align it, put it into the cryogenic chamber, cool down from room temperature to 4 Kelvin, and pry to have it still aligned. And so we developed this setup, and there are different materials with different shrinking coefficients, and so we design it in a way that the mechanical system in a way that it is like a self-centering system. That the metals are shrinking, changing the dimensions, but the system is self-centering. So one of my students was demonstrating this in one of international conferences and before like final test, and the feedback was that there is no way it can work. And then so these are like final stages of assembling before the final optical test, and few weeks later we demonstrated that the system actually worked, and we after many months of iterations, improvements, we demonstrated that we can fully operate this cavity at 4 Kelvin at this difficult to access wavelength, preserving this super high finesse. And now we are in the process of collecting the scientific data. So we already collected the extremely high quality data. So you can see, so these are, this is one of the molecular H2 transition measured at temperatures down to even below 5 Kelvin. And you can see that the signal to noise ratio is at the 10,000 level, despite the fact that we work at a deep cryogenic regime. So you may ask yourself that how come that we can measure molecular hydrogen at 5 Kelvin when the boiling point is 20 Kelvin, right? So we actually here we are working in a deep regime of vapor pressures. So actually the majority of the hydrogen is crystallized on the walls, and there is the very residual amount, but our system is so sensitive that we can reach extremely high signal to noise ratio. And now the preliminary analysis shows that we should improve our previous accuracy by at least 1 or even 2 orders of magnitude with this first step. But not only testing the quantum theory is like a physical opportunity for us. There are many other aspects of physics we can study with this setup. For instance, we already demonstrated very recently that we can measure extremely accurately in a fully optical way the H2 phase diagram. So these black points are our experimental points, and we really can access in the near future the H2 triple point, and that will be quite something to measure H2 triple point, which is an like important anchor point for calibration of thermometry at cryogenic conditions. We will measure this point in a fully optical way this way. We can measure, and these are experimental data, these lines, we can measure the orthopara conversion, the conversion between the symmetry of the nuclear wave functions in H2. There are other challenges at the interface of physics and chemistry that we can address with this setup. For instance, we calculated that the collisional effects that we already observe in our experiment at our temperatures are dominated for H2 by a single partial wave. So the H2 is due to its low mass is very atypical case, and already in our conditions we reach this fully quantum regime of molecular collisions. The collisions are really should be thought of as scattering of matter waves. Finally, also very recently, for the first time, we demonstrated that we can optically realize several SI units in a deep cryogenic regime with purely optical methods, using again spectroscopy of molecular hydrogen. So that was so this is this first experimental setup, and now let us look at this problem from the wider perspective. So this is the present best accuracy. With our new setup, we can improve this accuracy by 1, maybe even by 2 orders of magnitude. But the challenge is to fill this gap, to improve not by 2 orders of magnitude, but by 5, 7, 8, 12 orders of magnitude. And to do this, what we really need is to trap cold molecular hydrogen to enable using this whole machinery of cold atoms and physics. And for this reason, we are in the process of developing entirely new experimental setup, which is focused on trapping cold molecular hydrogen. So the idea, not much time to discuss this in details, but the idea is that we will effuse a small amount of cryogenic hydrogen inside high vacuum chamber, and then we will launch extremely strong optical dipole trap. So now we are in the process of developing, so we have 2 mirrors, this is that small, and we will, now it is happening in the lab, exactly in these days. We will inject extremely strong power inside the cavity. That will be over 100,000 watts of continuous laser power inside optical cavity. And despite that, as I said, H2 interacts extremely weakly. The power will be so large that we will be able to trap molecular hydrogen inside such an optical dipole trap. And our simulations shows that we should trap around 10,000 molecules, which is by far enough to do accurate spectroscopy. This is how the new setup, the H2 trap setup, looks like in the laboratory. We also do extensive theoretical calculations aimed at, so we ask ourselves a question, what can be done with hydrogen molecule at the fundamental level to improve accuracy? So we check the behavior of H2 in electric, magnetic field, in laser field. We are proposing new approaches to accurate spectroscopy, new approaches to further cooling, sympathetic cooling, and so on. And although I was asked to discuss the experimental context of the problem, I would like to devote 2 last slides to mention that actually my group, only part of the group is focused on the experiments. The other part is focused on theory, and very much related to molecular hydrogen. So one of the main branch of our activity are quantum scattering calculations, the collisional calculations for molecular hydrogen. So we do it in a fully quantum way, and then we validate our results very accurately on collision-perturbed molecular spectra. And our ambition is, on one hand, to test the quantum equations also for more complex arrangements such as molecular collisions, but also to provide useful experimental data to the community. So with this, our ab initio calculations, we populate spectroscopic databases, and for instance, they have been used for, our theoretical data were used for studying atmosphere of Jupiter. So we are trying to, in my group, we are trying to proudly follow the tradition of Wolniewicz. And last night I checked that we already published in recent years over 30 papers, original works on molecular hydrogen. Yeah, and this is we, and thank you very much.
Thank you so much, Piotr, for such fascinating talk. Any questions? Maybe none? We have not that much time, but nevertheless, I urge you to ask some questions. Piotr told me that if I'm standing here instead of sitting over there, it might be a lack of questions, but nevertheless, I believe in you guys. Short question, how you can measure pressure in this chamber? Because to know anything in very high accuracy, you need to have an instrument to measure it. So could you explain me such trivial question?
Yeah, so then, this is actually a great question. So then, it is no way that you can measure it with external meter. That there is an effect that although this is like a connected chamber, there will be a gradient of pressure, especially at low pressure regime. So we do it optically also. From ab initio intensity, I haven't shown this result, but we also demonstrated very recently that we are able to realize the Pascal SI unit at cryogenic condition with this, so we can calibrate the cryogenic pressure sensors this way.
Also short question. As far as I could understand, in your treatment of H2, you consider it as an electromagnetic object. And how far away are effects which are within standard model, but which are non-electromagnetic as weak and strong interaction contributions? Do you come to this threshold already, or it's still far away?
Yeah, so then we do not, in my group, we do not calculate the raw vibrational structure of H2 because the other groups, especially Krzysztof Pachucki or Edith Matthews, they are like world leaders and we don't like have even an ambition to compete with them. We calculate other properties. For instance, a hyperfine structure or the collisions. So then we work in a completely like, for instance, for collision, this is like electrostatic approximation. There are no other, as far as I know, the Krzysztof calculations or Edit calculations, they haven't reached the point when they have includes other than QED fields. It is the case for H atom, but not molecule.
Right, very last question, if somebody wish. If not now, let's move to the last section of today's, yes, applause for Piotr and his group.
Okay, thank you very, very much for invitation, and I'm a bit stressed because this is, firstly because this is a great honor to talk about Professor Lutosław Wolniewicz, which I think is sometimes my inspiration for scientific work, and secondly because in this auditorium there are many people who knew him personally. I didn't, so I'll try to tell you a few words about this person and why I think this person is so important for our institute and for science. So firstly, Professor Wolniewicz was born here in Toruń in 1930s, and he was living in this home. I met his sister, and when I was talking with her, she asked me to make a photo of her home because she's living near to Warsaw and she wanted to see how this home looks like now. And this is this building. So this is in our old town here in Toruń. Professor Wolniewicz had three siblings. First was his older brother Bogusław. He was famous Polish philosopher and logician. Second was Professor Wolniewicz. Third is Dr. Barbara Wolniewicz-Grzelak. She's a psychiatrist and psychotherapist. She lives near to Warsaw, and I think the less popular, the less known person was Andrzej Wolniewicz. He was an engineer and mechanic. He was living in Gdańsk. This was the youngest brother of Professor Wolniewicz. Okay, and this is not Professor Wolniewicz, this is his older brother, but I found this picture and I wanted to show you the father of Professor Wolniewicz because this is very important person, of course, and unfortunately he died in a German concentration camp in 1940 in Sachsenhausen. He was the manager of the law firm here, and even he was briefly a city councillor of our city. After graduating the high school, after high school, which Professor Wolniewicz finished in 1950, this was the very good high school in Toruń. It was the oldest one in the city. He started to study physics here, theoretical physics, but why I don't know. he chosen this, but in opinion of his family, he was the great candidate for Polytechnic because he has great mind in solving technical problems at home. So Professor finished the first step of his study here, and the second in Warsaw because there was requirement in this time to study in another center, to finish the second step of studies. And Professor Wolniewicz obtained his master's degree under the supervision of Professor Włodzimierz Kołos in 1955. The topic of this thesis was internal rotation of methyl mercaptan, and it was topic of quantum chemistry, but Professor wasn't interested in quantum chemistry. He wanted to study and to and he wanted to solve problems in quantum field theory because here he could learn from very good two theoretical physicists, Professor Rajski and Drzewuski, but unfortunately he had the problem with PhD thesis. Why? It wasn't because Professor Wolniewicz was too weak. No. It was totally different way. Firstly, he asked Professor Rajski for some doctoral thesis, and he had to generalize the theory of Professor Rajski, but Professor Wolniewicz proved that this theory was wrong. So the problem was wrongly formulated. He couldn't do PhD in this field. Secondly, he went to Warsaw to Professor Kulikowski. We know this manual for classical mechanics, which Professor Kulikowski is the author. And again, there was the same situation. The formulated problem was wrong, so he had to think about something else. So Professor Wolniewicz got 3-month internship in Dubna in USSR. There was Professor Nikolai Bogulobow. He was very famous physicist. But firstly, 3 months was too short to finish PhD thesis, and the second thing was again some problems which Bogulobow's collaborators proposed to Wolniewicz to solve was again wrongly formulated. So there was a problem, and Professor Wolniewicz came to Warsaw. Actually, he came here, but he started the collaboration with Professor Kołos. Professor Wolniewicz is here, and Professor Kołos is here. Professor Kołos was quantum chemist, but he needed someone who deeply understands physics, and the great person was Professor Wolniewicz. He finished before this. Professor Kołos went to Chicago to work in Professor Rutan group, which started something we called quantum chemistry, combinational chemistry now. So they were using very old computers to calculate some problems. He went there, And when he came, he started collaboration with Professor Wolniewicz. And Professor Wolniewicz completed his doctoral thesis under Kołos supervision in 1961. But what I know from my conversations with many people and what I suppose, what I think, Professor Wolniewicz wrote this paper mostly alone, and because this was very, very, this was a very complex, mathematically complex work, and this thesis was published in reviews of modern physics in 1963. It was very good paper. Most of this paper was Wolniewicz PhD paper, but unfortunately, in my opinion, unfortunately, we have here alphabetical order of surnames on this paper, and this will stay for all papers of Kołos and Wolniewicz. Yeah, but I think the order could be changed. Okay. I wanted to show you these computers. This is the. I wanted to show some how these computers looked like in this Chicago center. It was something like this. So it's not anything we know now from our home. And in Chicago, when Wolniewicz went to Chicago in 1963, he started to write the computer program based on his theory from this PhD. And what was very important was this, that the core of this program was Wolniewicz's theory. And the second thing, that in this time nobody in Poland knew what was the computer. Actually, I think we didn't have phones at home, and computers also. But Professor Wolniewicz, but in Chicago there was IBM computer, and they started to write the program to calculate these problems. And the result of this work were two papers, actually in one journal. Oh, sorry. In one journal. We have anniversary now in 3 days. In Journal of Chemical Physics, and in these papers there were these first calculations obtained from these computers, from this computer program which Kołos and Wolniewicz wrote. And there was this strange situation in which the dissociation energy was for hydrogen molecule was higher than Herzberg obtained from his experiment. So this was quite strange, but everybody thought that this was because of adiabatic approximation. But Professor Wolniewicz, few years later, alone, proved mathematically that the difference between these two energies, it's not due to adiabatic approximation. So the problem was somewhere else. And after 2 years later, Wolniewicz and Kołos went to Chicago again, and they improved the precise of these calculations. There was calculations with double precision, and again this energy was larger than this obtained by Herzberg in experiments. And 1 year ago, Herzberg improved his experiments. He improved this precision, and then appeared that Professor Wolniewicz and Kołos were right. His their result was good, and this was very important for this. What Professor Karwowski said, that they tested quantum mechanics on the fundamental level. 2 years later, Herzberg got a Nobel Prize, and he cited Wolniewicz and Kołos in his in this paper about this experiment. And later, when he got the Nobel Prize, he mentioned about Kołos and Wolniewicz in his Nobel lecture. So this was really important for us, because our institute, Warsaw and Toruń, became very popular. Oh, I have one anecdote to not talk about science only. Professor Wolniewicz had a brother, Bogusław, here, famous philosopher, and I heard from one professor that when Professor Bogusław Wolniewicz, philosopher, came to Philadelphia, he came to Philadelphia, and some group came to him, and they started to speak about physics. And he told that, I'm sorry, but I'm a philosophicant, so why you are speaking about physics to me? And they told that, oh, so you are not this famous Wolniewicz from Toruń? And yes, so Professor Wolniewicz was famous in USA. Okay, here we have something. What I was wondering, whose work was most important? Maybe this is a bad question, because as Professor Karwowski said, that there was very good synergistic effect, because Professor Kołos was very good organization and very good organizer, and he was of course very good scientist, but I think the core of these calculations and this program was thanks to Professor Wolniewicz and thanks to his work on this thesis. And I found in our archive of our university the opinion of Professor Kołos for Professor Wolniewicz, opinion of Professor Kołos of awarding Professor Wolniewicz to the title of full professor, and Professor Kołos wrote something like this: I would like to add that in our joint works, I generally assesses our contributions as roughly equal. Professor Wolniewicz always demonstrated great initiative both in undertaking new issues and in solving them. I would also like to mention that the paper of which I'm a co-author and to which Professor Wolniewicz's contribution was greater than me, has been cited over 480 times, but by 1981, and was therefore recognized by the Institute of Scientific Information in USA as a citation classic. This paper is famous now. This is the most cited paper of both authors, and it is just, I think it was interesting information. Okay, Professor Wolniewicz later, after this good collaboration with Professor Kołos, Professor Wolniewicz was working also with Professor Paul from University of Guelph, with Professor Dressler at Zurich, with Professor Hinze, Ubax, and Dalgarno from Harvard Center for Astrophysics. Okay, maybe I will speed up a bit, but I wanted to show you a very interesting thing. There was a thanks to Professor Karwowski initiative and with help of Professor Dębiński, Professor Szudy, there was a special issue of molecular physics. This is very good, very good journal. A few years ago, there was special issue dedicated to Professor Wolniewicz, and there are a few articles which are very interesting if you want to if you want to know something more about Professor Wolniewicz, his work and his life, I recommend you to find it and to read. And I wanted to say one more thing, because I heard once that Professor Wolniewicz was improving only numerical things. Firstly, I think it's not that true, because he was doing many theoretical, mathematically complex things, but he was very shy and timid, and he was speaking that this what he's doing is in Polish. To co robię, to takie rachcie. He was very mood and I think he didn't believe he's doing something really important. Yeah. Oh, okay. Okay. I don't know if I should tell about it, but Professor Wolniewicz never sought recognition of honors. He was once director of this institute, first democratically elected, and head of few departments. But he was always very modest. This is evident, for example, from the fact that in his joint works with Professor Kołos, his name was always at the end alphabetically, and from the fact that being less recognizable, he was not elected to the Polish Academy of Science, for example, but Professor Kołos was. And I heard few opinions that Professor Wolniewicz should go with Kołos should go the Nobel Prize. Of course, it's not so easy to say something like this, but it was very important result. So this question, of course, is open, but I know several persons who sent this letter to this Royal Society to give them Nobel Prize. Yeah, and I wanted to mention last few things, because we don't have time, that thanks to Professor Wolniewicz, our institute, after Professor Jabłoński, our institute started to be very recognizable. Firstly in Poland, secondly in the whole world. I found few papers, for example, authored by Professor Gumiński, who was very known chemist here in Poland. He wrote the paper about history of quantum chemistry in Poland, and there was, of course, the place for our group from Toruń, and Professor Wolniewicz was many times cited. Of course, not only Professor Wolniewicz. There was many professors. For example, Professor Karwowski, who's here, was mentioned also, and many professors from our institute. Yeah, and because Professor Wcisło told about Professor Pachucki, who is doing very precise calculations also, he got very good Minister's Prize once for performing quantum mechanical calculations of spectroscopic parameters for light molecules with unprecedented accuracy. And he told, after got this prize, he told that he's continuing the work which started Professor Kołos and Wolniewicz. And I wanted to show you, because of course citations are sometimes not good point to see how good was some scientist. But in Professor Wolniewicz's case, I think it's very good to see citations, because his papers was only one or two or maybe three co-authors in these papers. He was working mainly alone, sometimes with one or two colleagues. So you can see here, for example, 20 persons. So I think that this is very good. This very good point to see his citations and here's index, that his papers are still cited in the world. Okay, maybe it's too much. And I wanted to show a few examples, because that Professor Kołos and Wolniewicz were, thanks to their work and these famous calculations, Poland and our institute became very recognizable in the world. We can see, for example, here that okay, unfortunately it's in Polish, but their calculations and later papers of Professor Wolniewicz and Kołos and almost all quantum manuals for quantum chemists cites their work and their result. And here, for example, in the very interesting book about pioneers of quantum chemistry, Professor Wolniewicz and Kołos are also on many pages. Yeah, and at the end, because unfortunately I got a bit stressed and I'm speaking barely in English now. I wanted to mention that Professor Wolniewicz had also many PhD and master students from our institute. Of course, I don't know all of them, but this I wrote here. And at the end, I wanted to tell something about the family of Professor Wolniewicz and his passions. He was married to Zofia Wolniewicz, who was she was conservator of art monuments and the head of department of conservation of painting and polychrome sculpture at our university. He had one son who's mathematician and computer scientist in our university, and Professor Wolniewicz had many passions, but the first place was always for physics. He was also played the cello and he sailed, and he liked to ride horses. But I heard once, probably from his son, that after one incident in which he was injured by horse hoof, he stopped this. And Professor Wolniewicz unfortunately passed away at the age of 90 at home of his sister near to Warsaw, and the home of course, her husband, Janusz, who is very known Polish professor of psychology at Warsaw University. Yeah, so thank you very much. I wanted to say a few words. Sorry, I was a bit stressed and sorry for my English today. Yeah.
Thank you. Thank you very much. Please stay because I open the floor for discussion. So, yes, Professor Karwasz.
Just a comment. First paper by Kołos and Wolniewicz on hydrogen is from 30 August. Well, but it was published in Physics Letters, and I checked now, it is quoted only 6 times. But they already gave 7 significant digits in this paper, and Journal Chemical Physics obviously is quoted many more times. We wrote the contribution to the volume edited by Professor Schude and Karwowski. So we studied the story of this calculation of dissociation energy. And at the time of writing, there was a new experiment done by Dutch people with many digits, 12 or something like this, very accurate. And there was an old calculation from Professor Wolniewicz from 88. There was a new calculation from Pachucki, and Wolniewicz was better than Pachucki. You can look into this paper.
Okay, thank you for the comment. Any other questions to our speaker? Actually, I do have one. Like, okay, we are talking that the computers were old, like the power was low, but actually Did you see when you were looking through the sources, like, what about the program that was written in Chicago? Like, was it like, what was the language used? How much memory it used? How many lines? Actually, is it, you can find the actual program somewhere in the library?
No, unfortunately, no. I heard something about from his son that there was this big tapes, and
sure.
they were taking this to the plane, and firstly in Chicago, but later in Poland, that they were preparing this here and taking to USA. But I don't know the language, unfortunately. But this was on this, I don't know, very long tapes with some dots.
Okay, so, but yes, maybe you can comment.
Maybe I can comment on this. I heard one story of Professor Wolniewicz about this. He said that once they programmed on cards. They used Fortran and once Professor Rutan was present when they started, put this card to the computer reader, and Wolniewicz wanted to impress him with that it worked so well. But unfortunately, one card was missing, and then everything was broken. So he was for quite a long time upset because of this. And another story is that Wolniewicz, because of small memory, he used assemble language, which is very simple and saving memory, but rather difficult to use. And I think that at the University of Chicago, they keep these programs in archive.
Maybe yes. I have one small anecdote, or
please.
If there is no question. When I went to Professor's sister and her husband, I started to talk about his achievements. They didn't know about it because he was so mood. He didn't talk about it at home, and because his husband of his sister is very good scientist, professor of psychology. I told that, but you know what are Professor Wolniewicz's citations, and I told that it's more than 10,000, and they told that, okay, we knew he was good, but so good, we didn't know. Yes.
Okay, any more questions? Yes.
Another anecdote. Some time ago we wanted to document our colleagues. And we asked some colleagues, and we made interviews. They're on our site, and we wanted with Professor Wolniewicz. I asked him 3 times. He said, no, not with me. We made registrations of interviews with some scientists, you know, somebody of you, and we asked him 3 times to make an interview with him, and he said, no, not with me.
Okay, thank you very much. Actually, I do have one very last question. I see there are no other people asking to both professors here. So basically, from your point of view, at the very moment, if it comes to the accuracy, the ball is on which side, theoretical or experimental? Like the...
At the moment, the experiment is like 1 order of magnitude ahead, but there is a perspective, I think, the full non-relativistic contribution is already calculated another 2 orders of magnitude more accurately than the best experiments. So after calculating the other corrections, there is a prospect that the theory will be better in like 1 decade. So
Okay, any comments? Okay, thank you. If there are no other questions, I'm closing our colloquium. Thank you very much for all the speakers.